Radio isotope thermoelectric generators have provided electrical power for U.S. spacecraft for over 25 years. These generators are reliable, long-lived sources of electricity, and they are essential for spacecraft that must operate in the cold darkness of the outer regions of the solar system. Radio isotope thermoelectric generators fueled both NASA and military spacecraft, including navigation satellites, communication satellites, a meteorological satellite, and planetary and lunar explorers. Some of the most exciting space missions flown by the United States were powered by radioisotope thermoelectric generators. These spacecraft have included Pioneers 10 and 11. These were the first two spacecraft to fly to Jupiter and Saturn. Pioneer 10 has now passed beyond the orbit of Pluto, the outermost known planet in the solar system. The Pioneer 10 radioisotope thermoelectric generators have operated flawlessly for more than 15 years. The Pioneer 11 generators for more than 14 years. Viking landers. The first two spacecraft to land on Mars for long-term exploration were powered by radioisotope thermoelectric generators. These generators enabled scientists to obtain more than 6 years of data from the surface of Mars. Apollo lunar stations. Beginning with the second manned lunar landing in 1969, radioisotope thermoelectric generators were used to power all of the lunar surface experiment packages left on the moon by the Apollo astronauts. Voyagers 1 and 2. These two sophisticated spacecraft have defined space exploration in the 1970s and 1980s by providing spectacular photographs and other data from Jupiter, Saturn, and Uranus. The three radioisotope thermoelectric generators on each spacecraft have successfully operated for more than 10 years. All of these radioisotope thermoelectric generators have been powered by the heat given off from the natural decay of the radioisotope plutonium-238. Safety is the principal design criterion for these plutonium heat sources. In this videotape, we will see some of the safety tests that have been performed to evaluate the design of the newest heat source. This new source of power is known as the General-Purpose Heat Source Radioisotope Thermoelectric Generator. It has been designed, built, and tested for use on future space missions such as the Galileo and Ulysses. Galileo will explore the giant planet Jupiter, its 4 largest satellites, and its atmosphere. Ulysses will fly the first mission to the polar regions of the Sun. The new radioisotope thermoelectric generator shown in this cutaway is about 44 inches long and 16 inches across at the fin tips. It weighs about 124 pounds and produces about 300 watts of electricity at the time of fueling. The heat source consists of 18 individual modules locked together inside the thermoelectric converter. Each of these modules is encased in multiple shells to ensure its survival over a range of postulated accidents. The outer block-like structure, called the aeroshell, is made of a sturdy carbon-carbon composite material especially fabricated to survive the stresses and heating of re-entry into the Earth's atmosphere. A special graphite thermal insulator sleeve protects the internal parts from the heat of re-entry. A cylindrical graphite impact shell is included to absorb the energy of impact. The plutonium-238 fuel is formed into pellets and cladded with an iridium alloy, a metal that resists oxidation and other chemical effects. The overall safety goal of the general-purpose heat source is to ensure containment of the plutonium-238 fuel during all mission phases, including assembly, testing, transportation, the launch into space, and associated credible accidents. Typically, the kinds of accidents considered in designing a heat source include explosions of the launch vehicle and high-speed re-entry of the spacecraft into the Earth's atmosphere. An explosion can generate a blast overpressure and high-speed projectiles or fragments. Explosions can also lead to fires if the propellants ignite. Both explosions and re-entries will lead ultimately to impact as the heat source hits the ground or water. More than 9 years of engineering and safety tests and analyses have been performed on the general-purpose heat source, making it the most studied space heat source available. This tape describes some of those safety tests and compares their results to those of similar environmental tests conducted on the Titan Centaur launch vehicle, used to launch the 2 Voyager spacecraft. 12 explosion tests simulated the blast overpressure that might occur in an explosion of the launch vehicle. These tests spanned the pressure range from 200 pounds per square inch to 2,200 pounds per square inch, beyond the range expected in a Titan Centaur explosion. None of the fuel capsules was breached by overpressure. A total of 20 projectile impact tests used 3 types of projectiles and 4 different targets. These tests were designed to span the range of probable projectile velocities associated with a launch vehicle explosion. Initially, 50 caliber aluminum bullets and 30 caliber titanium bullets were fired into heat source modules and fuel capsules to test the response of the heat source to collisions with small projectiles. These tests showed that the threshold for direct mechanical damage of a fuel capsule ranged from almost 1,400 feet per second to more than 1,800 feet per second, well beyond the projectile velocities predicted for a Titan Centaur explosion. 4 flyer plate tests evaluated what would happen if a plate-like projectile hit the fuel capsule flat on. For this test sequence, the simulant fuel capsule is heated to the proper temperature and lowered from the furnace so that it faces the aluminum flyer plate. The plate is driven into the fuel capsule by an explosive charge mounted on the back side of the plate. Depending on the thickness of the plate, the velocities for cladding damage ranged from 885 feet per second to over 3,800 feet per second, well beyond the flyer plate velocities predicted by Titan Centaur tests. 2 tests were run in which aluminum alloy plates 0.8 of an inch thick or greater were propelled edge-on into heated simulant fuel capsules at 465 feet per second and 3,000 feet per second. In the first case, about 1/4 of the simulated fuel was released, and in the latter case, it was all released. However, these test velocities are well beyond the flyer plate velocities predicted by Titan Centaur tests. Following an explosion or re-entry, the heat source components will eventually strike something, be it sand, water, or harder objects. Other tests evaluated the response of the heat source modules and fuel capsules to such impacts. Most of these tests were conducted in a special gas gun built at Los Alamos. The tests showed no breach of the cladding at the terminal velocity of the modules. For the most likely targets, sand, soil, or water, the capsules have demonstrated a capability to survive impacts at velocities in excess of 820 feet per second, well beyond any calculated impact velocities associated with Titan Centaur accidents. If a launch vehicle explodes on or near the launch pad, it may produce fires from the burning of any residual propellants. One of the most severe of these fires would result from the burning of the solid propellant used in the Titan Centaur boosters. To simulate such a condition, 2 specimens, a bare fuel capsule and 2 capsules in an impact shell, were placed next to the maximum quantity of Titan solid propellant, a cube 3 feet on each side. The propellant was ignited, producing a violent flame zone about 15 feet long with temperatures above 3,700 degrees Fahrenheit. The results of the test showed that exposure to this severe fire would not cause any release of fuel. A number of tests and analyses assessed the response of the heat source modules to the heating and stresses of an accidental re-entry. Among the tests was one in which the aeroshell was exposed to re-entry-like heating in the giant planetary facility at NASA's Ames Research Center. This and other tests and analyses showed that the heat source modules will survive re-entry. The tests described in this tape are part of an extensive, ongoing program to qualify the general-purpose heat source for future missions. The versatility of this modular heat source will make it a useful fuel for planetary and other missions throughout the rest of the century.